Okay, for this video, we will have a seismic drift checking. Okay, so we will have seismic drift checking. So I will open the manual use for 18-story building. So we have here checking of seismic drift. Okay, now we will open the model. So we have here a model like from previous discussion. So the 8-story L-shaped building, ETABS model revision 3, we will open this one. Or this is just the model we made. Okay, so I will open the software, then go to File, Open. I will just wait a while. Okay, then this is the model. I will just click the open and let's say I will unlock this model. Okay, so 3D, then to check the drift we need to have a seismic drift base shear. This is different from the design base shear. Okay, so what we want now is the modal participating mass ratios and modal load participation ratio. Okay, so this one is what we are looking for, the mode 1 and mode 2, and also the dynamic participating mass ratio. So okay, so I will run the model, or you can check model if there is a warning. So let's say I will just click that one, then the model is running. Okay, no warning, then we will proceed to running analysis. So this is the run analysis, or you can go to analyze and click this one. Then go to table, display, show table. So go to, if you want to know the base shear, you can go here, go to seismic, then we will go to analysis results. Model result, then this two, you have to click this two. Okay, so we will notice that the dynamic participating mass is above 90%. So the requirements from the code is 90%. Okay, so we will go to modal participating mass ratio. So we have this value from mode 1. So this is the vibration properties of the building, mode 1 and mode 2. So you will notice the period for mode 1 is 1.996, and the direction of the vibration is along UY because it's 0.6212 participating. So let's say I have here a plan. This is X and this is Y. So the movement of building for mode 1 is along X. Okay, so you have here a global axis. Then for the X axis is 0.0186, so almost 1%. So you will notice that 1% compared to 62%, so the movement of the building is in translation. This 1% will not is negligible compared to 60% along Y. Okay. Then for the mode 2, the vibration is along X and the Y direction is only almost 4%. So I can assume or I can generalize that the building is in translation for mode 1 and mode 2. And for the mode 3, you will notice that the mass participating ratio is so small. Then the rest iteration go here, and the sum of participating masses is here at the bottom. So that will equal to, it will just equal to the one we have here in modal participating ratio, this one. Okay, so that value. Okay, what happened to my desktop? So that is the value, and this is for the some UX, some UY, and some UZ. Okay. Okay, so we will now, what we want is our seismic drift base shear. So what we will do is we will take this time period for mode 1 and mode 2, and from my Excel, this is the load combination. So this formula where's my formula here? So I have my formula here. So the base shear, this one, let's say I have this base shear, so it will give you seismic base shear. So utilizing the time period from mode 1 and mode 2. So you will have now Vx, that is the base shear for the x-axis, knowing that we have seismic mass, and we have this value CV, then the I, importance factor, and the R. So you will now get the Vx. Same for the Vy. Okay, so this one is, I will just delete this one. Or the simplest way, I have the simplest way, I will just define the seismic drift. So I will go to the drift. So we have a seismic drift for base shear using the time period 1 and the time period at mode 2. So what we want is we will convert the static, we will find the static base shear and we will generate this response spectrum, drift X and drift Y. So the one I did is long method, but now we will have a short method. Then what to do is I will just snip this one. Okay. Then I will define another load pattern. Let's say I have here EX drift seismic. I want to have that type because I will sorry. So I will just add. So I will repeat. Okay. So EX drift, then seismic, and UBC 97. Then I will just click add. I want to add this load pattern. Then for the y-axis, I will just rename it y and add new load. So I will just review the given here for the so we have value x plus eccentricity ratio is 0.05. Then I will have CT roof and ground 8.5. Then I have here SD 0.4, then A 6.1, and importance factor is 1. So we'll just input here at X 0.05. Then this one, that the time period at X, we will use user defined. So for the user defined, we will have at X, the participation is in mode 2 at X. So we will utilize this 1.651. Okay, to give the 7. Okay, then this one is roof, this one is ground floor 8.5, and SD, this one is, what do we have, A, this one is 6.1. Okay, and then the direction is X, so we will have this value. Okay, at X, your mode is at X, this one using mode 2, and we overwrite this one, this value. So this value will give you this earthquake will give you a base shear for drift. This one will give you base shear for design. Okay, this one will give you base shear for serviceability check, earthquake, okay, seismic drift. Then for the Y, we will have here modify. Then I will just select the Y direction plus eccentricity. Then time period is, I will just use the time period of mode 1 because knowing that this is for along y-axis. Okay, so I will have this value 1.996. This is 1.996. Okay, then the top story is roof and the bottom story is ground floor. Then I have overstrength factor R. Then I have here SD, and this is zone 4. Then I have here A. Then I have the distance is 6.1. Okay. Then I will just click OK. I will just click OK. Then I will run the program. Then I can easily get the value to be used for seismic drift. Okay, so if I input the value here from this table, display, show table, then we'll go back here to the base here. This is seismic, this one. Okay, click OK. Then I have the design base here, and I have the seismic base here, this one. Seismic base here for drift checking. Okay, now this value for the design utilize this 0.721 seconds. Now this is the weight of the structure. This is the weight of the structure, and then this is the base shear of the structure. So the first two is for the design base shear, design level earthquake. Then the second two is for the seismic drift base shear to be used. Okay, you will notice that the design base shear is larger than the seismic base shear to be used for the drift because of the time period. Now, if you notice, if you want to get this value 7487.225, this value can be done using weight of structure. So I will use the Excel. Okay, I will just show this value. What is, so start from here, CVIRT. Okay, then I will just use this Excel. Your CV is, what's this value? So okay, so we are here. So that is 0.96768. Then the value of I is 1, this one, the value of I. And the value of your R is, knowing that that is 8.5. And your seismic weight is this one. Okay, your seismic weight 108,975. Let's say 108,975.9239. Okay, then your time period for along X, let's say, or we have here time period base shear along X, let's say this is Vx, What is our direction? Okay, so let's say I don't I will delete this one. So because we have here already a time period and we have the direction and input in the load pattern correct from the modal participating mass ratio. So we have here 1.657 and we have here for Vy we have time period of 1.996. So measure X basically this is for base year X. So we will match this for the dynamic. Okay, that value is also this value. Okay, we just use this formula utilizing the time period. Okay, and then the second one is this value. Okay, then we will proceed to match. We will scale 100% the base shear from the static. So this is the static base shear for the seismic drift, and we will scale it to match with the dynamic base shear to use for the drift checking. Okay, so what to do is you will display show table. Then we have here from the analysis results, and we have here structure results, story forces. Then we have location bottom. Then we have here second floor bottom. So the second floor bottom representing the ground floor. Okay, so we are, for example, this is ground and this is second floor, and then third and up and so on. So we are we have here mass at second floor, mass 3, and then we want the value acting here, the base shear here. Okay, that's why we have you will notice that this is bottom and this is the top of second floor. Okay, or that value is equivalent to ground floor top. So but I just want to use the second floor bottom, so I will just export this to Excel. Just export to Excel, then from this, so this value is our seismic drift base shear, and we want to match it to this pattern, or to this case, the RSA drift X max. So what to do is put equal, so static, I will just say negative, then I will just input it here. So static over dynamic equivalent to 1, and the other one along Y, static over dynamic, this is for the dynamic. Okay, this is 1.0. So it's already scaled. In case that the value is different, for example, I have here let's say I have this value. So, static over dynamic, I have this value, let's say 0.883. Okay, so this is just a number to multiply to the scale factor. So, let's say I have 0.83. What to do is, or let's say I have here another value. Let's say I have here 9,000 or so 0.83 and 0.69. Let's say, but for this time, we already have a correct scale. So you will go here, load case, then you will click this drift X. Then to match that value, you have to multiply it by 0.83. Let's say 0.83. Okay. Then you will run this one. But for now, we already have 100% scale. So what to do if I want to go back to default value? Let's say I have here 9.81 mm per seconds, divide 8.5, that is the default value. Then I will just rescale the value. So let's say 9810. So I times R. So your I is 1. I is 1. The numerator for this one, IG all over R. That is the default value. So I is 1, G is 9.81 meter per second squared. So but using mm, you have 9810 all over 8.5. IG over R. This is the value. Okay, but this is just scale value. So I will just rerun. Then I will do the scaling. So from the default value to scale factor, so story process, then I have this value. So let's say I will just copy this one to my Excel. Then load. Where's my Excel? Okay, paste. So let's say this is the value 5568. So that value is this. Yeah. Then I have here static shear, static all over dynamic. So that is your scale factor. Okay, so I will get this one 1.344 and 1.252. So I will go back here. My intention is to match this. I will match this value to this value. That is my intention. Okay, that is why I am scaling. Okay, so the scale factor is 1.344 and 1.252. Define load case RSA drift X. So I will just multiply this by 1.544. Then I will just click the tab. Then click OK. Then this one is times 1.252. Click OK. Then I will just click OK. Then I will just rerun the model. We don't need to unlock the model. Okay? Because the one will update is for the seismic drift cases. Okay, so display, show table. Then now going back to second floor bottom, So this value, what is my scale factor? Oh, my scale factor is 1.344. I input 1.544. Anyway, the value for y direction is the same, and for this one, this is not the same. So I will just export this one. Let's say I did a wrong procedure, and what to do is I will just to correct this one. So static all over dynamic. Okay, so 0.87 my new scale factor. And the other one is 1.0. This no need to scale the along y-axis. So for the x-axis, you need to multiply it by 0.87. Okay, then before I multiply this one by 0.87, I will review my design base here. This is my design base here. Or if I want to review or to correct also this base here, so this is one for drift, and then for the design, I will now do it static all over dynamic using SRSS. This one, it's already scaled, so I will just, and the other one is this. So you will notice that for the SRSS, this is for the design base here, you have value along x, you will match this one also at x, and at y you will match this one. Okay, that is for the SRSS. This is for the design base here, dynamic, and then this is the design base here for static. Okay, now for the design base here, static and dynamic for the design, so you will multiply this one also, but it's closer to 1. So let's say I have here 0.87. Define load case diff x. This is multiplied by 0.87. Then if I want to also to do the scale for the design base here, so I will just multiply 1 and 0.98 this value. So you will go here, response spectrum here, and you will multiply for U1. This is times 1.0, so that is just the same value, and here this is 0.98. Then click OK. That this value will be used for frame analysis and design for the software structure. So for the frames and shear walls. Okay. Now this value will be used for the foundation analysis and design. So if you want to scale this one now, because we will be using this value for the file foundation check and design, and we will count the number of files to use, we can also scale that one. Okay, so that one is this. For example, this is your scale factor. So static, your static here all over dynamic. This is your dynamic. it's equivalent to 1. Let's say this one and this one. Okay, so this value is already scaled and it's closer to 1. Okay, if you want to utilize 90% of base year, you have multiply this one by 0.9. Okay, but now we will do the 100% base year. Okay, so we will go back to drift check. So we'll go back to drift check, but we already scaled the dynamic design base year. So I will just show the story forces and I will just review the value for the static drift. So that value and this value is closer to 1 or closer to 1 if you divide that one. Okay, 7487 and 748. So I will say that we have now a scaling factor is done. Okay, so I can review. So it's closer to 1. Then the other, it's closer to 1. Okay, so now we will proceed to this. I will just close the Excel. Let's say I will just close this one. Then I will go back to load combo. What to check is this load combo. So we have here drift X. We have this load pattern for the seismic drift. So RSA drift X and RSA drift Y. So we are interested in this load combo drift X and drift Y. So from the table, from my Excel here, I have here seismic drift along X, this one. Then you will input the values here. Values from input, from a tab, so you have control table, analysis, results, displacement, diaphragm, center of mass. Okay. Then you will input here the time period or control table, results, displacement, diaphragm, center of mass, displacement. Then you will go to load case. I will just click the D drift X max. You will notice for the drift X max, so 80, and the minimum value is, so either of the two, you can check these two. So let's say I will check drift X max. I will just export this to Excel. Okay, then I will copy this one, Control C, then just paste here. Okay, then for the Y, I have this value you can check either X max and X min. Also for drift Y max, we'll have this value. We'll just export to Excel. Then I will copy this one, Control C. Then go back to seismic drift along Y. So I will just paste here. Okay, so here there is the drift ratio is more than the allowable. So our allowable is 0.02. This is from code. Based on the code, we have here a delta M. We will utilize the delta M. Okay, delta M is 0.7 times R times delta S. But the delta S is what we get from the ETABS. So this is the delta S. This value is the delta S, or this is the static. This is elastic drift. This is elastic drift. Okay. Then you will convert it to delta M. So the delta M is the inelastic drift. Okay, so this is the delta S, this is the drift ratio, this is the drift, so 80.66 at roof. So the roof is small, so we can ignore this one. So we will go to roof. That is 71.897. This is the drift. Okay, this is the drift from upper to lower level. Then this is the delta S, or this is the drift ratio. So you will just subtract this one. So 71.897 all over 64 divided by your story height. So it will give you 0.0025. Now the drift, if you convert that to millimeter, so for example, I have this sketch. So I have this sketch. Okay. So for example, I have this 71 in this level, 71.8 mm, and at this level I have 64. So this is 64. Okay, so you will notice here that, or you will have this difference equivalent to this value, and the ratio is this one. This is just a delta 2. Let's say we have here delta 2 equals to 71.897, and you have here delta 1 equivalent to 64. So you have this value, or this value, this is just a delta 2 minus delta 1 all over h. This h is your story height. So that value, that drift, this is the delta S. Okay, so we are in the elastic drift. Now we will go to delta M. So your delta M is this one. This is in elastic drift. So that is just equivalent to 0.7 from the code times R times delta S. And that is not to be greater than the allowable. Na your allowable is 0.02 at this case because your time period is more than 0.7 seconds. Okay, so this is clear. So you will notice that the every center of mass we have a small small difference in the drift of mass 1 and mass 2. Okay, so but if you deal with these ratios, you will not notice, or you will not imagine what is the what drift, or what lateral drift, what is the value of that drift, or what is the quantity. But if you put the table like this one, you can imagine now the drift we're talking about. Okay, now because for example this is, I don't have that one, so I will just deal with this one, so I cannot imagine these values. Okay, that's why I put this column. Now this value will not be greater than 0.02. Okay, so check, we have here a value. This is the delta S times 0.7 times R. Then I have here a comparison. If this one is less than 1.09, I did a, for example, this is less than 1. This is pass. So this is for your checking. So I just divide the demand. Let's say this is the demand or the actual all over the allowable, and it will give you this value. And I should say this is pass. Okay. Now for the y-axis, we have this value. So there is a red here. What to do is you can increase the size a little bit for the columns. But if you will notice this value, you will find out that this value is exceeding the allowable. So this one should be 0.02 or less than. So along y, let's say this is along y, you can increase the stiffness along y. So if you go to the model, and I will investigate the plan. So I will increase the stiffness of the building along this axis, but that's a little bit increase of stiffness. You have to be careful, because if you cannot increase, if you increase the stiffness here alone, your building will somehow rotate. Okay, so you will have to study how to increase this one, or you can increase the size of this one. For example, this is for initial. For example, that is a, let's say 500 by 1000. You can put now 1 2, for example, for this dimension. Okay, to increase the moment of inertia or the stiffness. Okay, then after doing that iteration, I will just input the values here and you will have to pass this one. So for now, for this tutorial, we don't do the iteration or I will not do the column resizing. You have to do it for yourself. This value is 600 by 800, so I can put a 600 by 900, or I can increase I will just increase the A prime of C from foundation up to fifth floor. I have another concrete strength. Okay, so I will not resize the column. Okay, so this is the end of the story drift checking, seismic drift checking. Okay.